Okay, so in chapter 11, we are going to be talking a little bit about probability. And chances are that's a term that you have heard before. The most common definition of probability is the chance that some event will occur. So, a few basic just terms that you're seeing here that you'll hear referenced as you go through. A lot of times we use the results of an experiment to determine the possible outcomes that can occur. Outcomes are just the results of the experiment, the things that could happen, and we look at the probability of particular events, which are just a group of possible outcomes. And we're going to talk about two different types of probability here. Empirical is one that's based on data. It's also called experimental. And theoretical is one that's just based on possible outcomes. And it's more of a mathematical approach. All right, so we're going to start with empirical. And these are pretty straightforward. It's really the equivalent to calculating a relative frequency or like a percentage that corresponds to a particular event. So, what you want to think about with probability is you always have to know the total number of possible outcomes. That might be the total number of people included in your study, it might be the total number of boats in this case, but you're always going to need to know the total because the way you calculate a probability is you take the number of times the particular event can occur or has occurred, and then you just divide that by the total. So, anytime I'm going to be looking for a probability, the first thing I do is I make sure I understand what my total is. So, for example, in this case here, we're looking at the last 30 boat rentals. Okay, so right off the bat, I'm going to go ahead and note that my total number of outcomes here is equal to 30. And if I wasn't told it there, notice I could calculate it for myself by simply just adding up the number of different possibilities that we have, right? 14 sunfish, 10 kayaks, and 6 rowboats, right? That also shows me that the total for this experiment is equal to 30. All right, 30 boats to choose from. So our questions here determine the probability that the next boat rental is a sunfish. All right, now typically how these things are written, and you see it in your definition up here as well, capital P shows you're finding probability, and then whatever event you're looking at is written in parentheses. All right, and all I'm going to do is use my definition up here. So this says to find the probability, I do a fraction or a ratio. I always take the total and put that number on the bottom of my fraction. And then what I do for the number up top is I look at how many times this particular event occurred. All right, 14 of the rentals were sunfish. So the probability that the next boat rental is a sunfish is 14 divided by the total of 30. All right. Now, pay close attention to how your answers should be reported. Notice this says express as a fraction in lowest terms. So don't make that a decimal here. All you want to do is see if it can be simplified. Both of these 14 and 30 are divisible by 2. So this would simplify to a fraction of 7/15. And that would be the probability that the next rental is a sunfish. All right, and so whatever event I want to look at, I can use this exact same rule. All right, here I want to know what is the probability that the next boat rental is a kayak. And so I'm going to use that same rule, right? I'm going to set up my ratio or my fraction. Total goes on the bottom. And then this time, the event that I'm looking at specifically is that I get a kayak. So I take the number of times that occurred, there were 10 kayaks, and just divide it by the total. And then again, this one says fraction, so all I want to do is simplify if I can. 10 and 30 are both divisible by 10, so this will simplify fraction in lowest terms to 1/3. All right, and the rowboat would be done the exact same way. So I'm going to leave that one for you to finish out. All right, and so what you want to remember is anytime you have data, right, information, it might be in a table or it might just be in words like what we saw before, information about something that happened, you can just use it the same way to calculate a probability. The key is you always have to have your total. So as soon as you see that you're going to be looking for a probability, the first thing you want to do is take your data and determine the total, in this case, the total number of animals that were treated. So if I add up the number of dogs and cats and birds and rabbits, I get a total of 105 animals. And I got to have that to do probability. Once I have that, then I can use the same rule. If I want the probability that the next animal treated is a dog, right, set up my fraction. The total goes on the bottom, and then I take whatever event I want to look at. This says we get a dog. Take the number of times that occurred. And then if you can simplify, which we can here, 45 and 105 are both divisible by 5. That would simplify to 9 over 21, and then I can do it again, right? Because 9 and 21 are both divisible by 3. So this would simplify all the way down to a fraction of 3/7. And I would do the exact same thing for B and C, right? Take the number of cats divided by the total, take the number of rabbits divided by the total. All right, so we're going to look at one more here with empirical probabilities where we're given the number of each type, and then we're going to switch and talk a little bit about theoretical. All right, so again, anytime I'm going to be working with probabilities, I know I'm going to have the total for the experiment. So in this case, we're testing a drug, a high blood pressure drug. The drug is given to 500 total individuals. All right, and remember, anytime you're not given the total, you can compute it yourself if you just add up the number in each group. All right, so I've got 379 for reduced, 62 for unchanged, 59 for increased, and that would also show me the total here is equal to 500. All right, so part A here, find the probability that the person's blood pressure is reduced. All right, probability says, right, set up our ratio, total goes on the bottom, and then the one I want to look at here is that it was reduced, all right, that's right here. So the number of times that occurred was 379, and this one tells me to report my answer as a decimal rounded to 4 places. So this time I'm going to go ahead and take my calculator out. 379 divided by 500, and that gives me in decimal form a probability of 0.758. All right, and again, these rules always work the same way. So if I want to do B, find the probability that the person's blood pressure is unchanged. All right, the rule doesn't change. Total goes on the bottom. The one you want to look at here is unchanged. That happens 62 times. All right, so basically how many for the event divided by the total, 62 divided by 500 here in decimal form is 0.124. And the same thing would happen for the increased. Okay, so pretty straightforward once you understand, what this rule looks like. Just for whatever experiment you're looking at, make sure you identify your total and then use that information to calculate the probability that you're asked for. Now, you do want to be careful. Sometimes you're asked to look at a particular group, and that might change your total a little bit. So just to look, for example, at like the first part here, we'll do part A. All right, a medical researcher administers a treatment to 200 patients, right? So right off the bat, you would say, okay, my total is equal to 200. The patients in the study are categorized by blood type, all right? And then the researcher observed a favorable outcome, and we're given information about that for each group, all right? Now, what you have to be careful about here is when you read the question, determine the probability of a favorable outcome for those patients with each type of blood. Okay, so what I'm looking for here is the probability that it's favorable, right? That's the event that I want to look at. But when you're given a particular group like this, you only want to look at those here with blood type A. So because of that, my total would not be 200. If I'm only looking at blood type A, then I would only look at the group with blood type A. And that group has a total of 80, 24 of which had a favorable outcome. All right, and then that would simplify to 3/10. And the same thing here. All right, if I'm told to look at a particular group, right, I'm still doing the probability of a favorable outcome. All right, that's the question here. But if I'm only looking at blood type B, then again, I'm not choosing from all 200. I'm only looking at the 22 with blood type B, so that's my total, 11 of which had a favorable outcome. All right, so just watch for that. If, again, you're asked to do a probability, but only for a particular group, that might change from the overall total to that smaller group. All right, so again, everything we've done so far is what we call an empirical probability. That means it's based on some experiment that was run, right? Data that's been collected, something of that nature. And the law of large numbers, right, essentially says if you look at something that happens over a long period of time, the more you look at, the more likely that probability is going to be accurate. All right, now, theoretical probability, on the other hand, instead of looking at the results of an experiment, it just looks at, okay, what are the possible outcomes for the experiment, and it uses that to determine the probability. Now, a few things to note here, some important facts. A big one is this one right here. Anytime you calculate probability, you have to get something between 0 and 1. Okay, if you're finding the probability of an event and you don't get something between 0 and 1, you get like 1.47, it cannot be right. Don't enter it. Go back and try again. All right. Others here, a couple of special cases. If something can't happen, if it's impossible, its probability is equal to 0. If it must happen, right, like it's certain, then its probability is going to be equal to 1. All right, so when you think about probabilities, you can kind of think about them like on a scale, right? Possible probabilities are going to range from 0 to 1, all right? Where 1 is something that is certain, it will happen no matter what. 0 is something that is impossible. There's no way that it will happen, all right? And then, of course, the halfway point here would be a value of 0.5, right? Like a 1/2 probability. And so, you know, values that we get for probabilities that are closer to 0, these are things that are more unlikely to occur. Values, especially as they get closer to 1, are going to be values that are likely to occur. So you can kind of think about it on a scale, but this also shows you why it has to stay between 0 and 1. All right, so let's look at a couple examples here with theoretical, and then I'm going to give you some examples that I want you to go through and try on your own. All right, so theoretical probability is written a little bit differently, but it's the same concept of count the event and divide by the total. All right, the main thing here is because we're not basing it on data, what we're counting is going to be the number of outcomes in our particular event. Not how many times did it happen, but how many times could it happen, possibilities. And then probability is always dividing by the total number of possibilities. All right, so a fair die is rolled, all right, and we're asked to find some different probabilities. Now, when it's theoretical, an easy thing to do is to go ahead and write out what those possible outcomes are before you start. So if I'm rolling a fair die, right, 6-sided die, these are my possible outcomes. And all I want to do to find the probability, all right, for example, part A, find the probability that you roll a 2, is set up my ratio, put the total on the bottom, right? There are 6 possible outcomes. And then if I specifically want the 2, then I just come up here and I say, okay, how many outcomes are included? The 2 is one possible outcome, and so its probability is 1/6. All right. B, I want the probability that I get an even number, right? Total on the bottom. And then whatever your event, just come up here and count, right? Even numbers are 2, 4, and 6. So the number of outcomes included, the number of times it happens, right, is 3. And of course, 3/6 would simplify to 1/2. All right, then all these are going to work the same way. The probability of a number greater than 3, that's part C, right? Total on the bottom. If I want a number greater than 3, all right, that happens with 4, 5, or 6. All right, so 3 possibilities there. And then again, simplify if you can. And then D and E are to show you our special cases. All right, the probability that we get a 7, right? You look at your outcomes up there, 7's not a possibility, right, on a 6-sided die. So as soon as you see that your event can't happen, that it's impossible, then you just state the probability equal to 0. And for the other extreme, right, a number less than 7, well, that has to happen. Everything on a die is less than 7. So as soon as you see that your event is certain that it must happen, you know it's going to have a probability that's equal to 1. All right. And again, this works the same no matter what you're looking at. So I'm going to look at 1 or 2 here and 1 or 2 on the next example, and then I'm going to give you some to go through and work. And of course, you can always check the others using the completed notes. All right. But the key here again is to make sure that you're looking at the proper total, and then it's always count the event, divide by the total. All right. So we have a table of information here. And the table of information is based off 9 different bird types and their food preferences. All right. So part A, all right, all of these are put in a bag on slips of paper. That means each one has the same chance of occurring, and 1 slip is to be selected. So determine the probability in part A that the slip of paper contains a type of finch. All right, so we're talking about possible bird types. All right, you've got them all listed right here. So the total different types of birds is equal to 9. All right, total goes on the bottom. And then if we specifically want to look at a finch, all right, that could happen with this type of bird here, that's a finch, or with this type of bird here. So the number of possibilities for the event, right, a finch is 2, and then divide that by the total. Our probability of a finch is 2 nights. All right, now sometimes you might be asked to pull some different things together. So let's skip down here and look at part C. All right, this one now is looking at their food preferences. So it says, find a bird that has a low attractiveness to peanut kernels, right? So that means in this first column, it's going to have a low. And a low attractiveness to cracked corn. So here it's going to have a low. And a high attractiveness to the sunflower seeds. All right, a low attractiveness to peanut kernels, a low attractiveness to cracked corn, and a high attractiveness to sunflower seeds. All right, so I'm going to look through my rows here, and I'm going to find where that occurred. Right here is a low, low, high. Here is a low, low, high. I'm just seeing where does this event occur, and here. So probability says put the total on the bottom, right? 9 different possibilities here. This event looks at 3 of them. And then when I simplify, the probability would be equal to 1/3. All right, so I'm going to leave the others for you to look at there. The last example here deals with a deck of cards. And because people don't play cards as much now as they used to, you have a nice little diagram here to show you what the different types of cards are, and you'll need to use this as you go through and do your homework. But again, it's the same concept, right? You want to understand your total, right? If you're going to do probability, you got to have total. And then how it's broken down, we've got this all included in our diagram here. We're going to select one card. And again, we're asked to look at some different probabilities. All right, so let's do A. Find the probability that you select an 8. All right, so again, all you're going to do, use the same concept here, right? The total always goes on the bottom. 52 total cards. You see them in your picture. And then if you look at the possible 8s, there's an 8 in every one of the 4 suits. So the event contains 4 outcomes, and you're dividing by a total of 52. All right, and if I simplify this, these are both divisible by 4. This would simplify to 1/13. All right, now part B here shows you kind of a little special case, and this is something that's also discussed right here. When the word not is in front of an event, this is a lot of times called a complement. What you can do is you can take the probability of an event and subtract it from 1. So like part B here says, find the probability that I get something that is not an 8. All right, well, what I can do is when I see that not in front, I can say, well, you know what? That's the same thing as 1 minus the probability that what I get is an 8. So that means if the probability of an 8 is 1/13, then the probability of something that is not an 8 is just 1 minus that. All right, and then depending, you know, again, if you want it in decimal form or fraction, I'm only fraction here. 1 is 13 out of 13. And if I subtract 1 out of 13, then I'd be looking at a probability of 12/13. Anytime there's a not in front of it, you can use that to flip it around. Just subtract the event from 1. All right, so let's do one more here, and then I'm going to leave the others for you to fill in. Let's come down here and do D. The probability that I get a jack or a queen or a king. These are called face cards, or this is calling them picture cards. But and so what I'm going to do here is the same thing. I'm going to put my total on the bottom. And then I'm going to come over here and I'm going to count, all right, the number of outcomes for the event. So the picture cards, the jacks, the queens, the kings, right, are right here. And so if I count that, I'm going to see that I have 12 different face cards, jacks, queens, or kings. So I take the number of possibilities for the face card, the jack, the queen, or the king, that's my event, and I divide that by the total. All right, and then each of these is divisible by 4, so this will simplify to 3/13. All right, so I want you to go in and try to finish out the examples in the notes. All right, use my completed notes to check your work. And then before you jump in and really start trying to do your homework, I want you to go into the practice and try at least these 4. Use the help tools if you need them, because this will take a little bit of getting used to. But remember, the probability is always just going to be the event divided by the total. All right, and so once you've done some work in 11.1 and you're feeling pretty good about that, then you're going to come back and I'm going to have a separate video to walk you through a couple more things in 11.4 and 11.7.